Hey guys, so I'm hoping at this point now everybody has electricity and water and Wi-Fi, and that you all are doing well. To say that the governor's announcement yesterday broke my heart is a huge understatement. I was really looking forward to seeing you guys, even if it was only going to be for a week before the school year went out. And sadly, it does not look like we're going to get that opportunity. For my seniors, I do hope I get to see you sometime soon. And I will be reaching out to the seniors later on. I want to make sure that you guys know that you can reach out to me even after your graduation if you need me for anything. So I'm really kind of disappointed with how things have turned out. I know that you guys are probably much more disappointed than I am, though. We are in the third unit. We just started. We did half a set of notes last week on Monday, I believe, is when I did this, and then so I'm going to complete the second half today, and we're just going to keep pushing forward. Try to get this class wrapped up by May the 8th. Now, one thing I do want to point out is that if we do not complete everything by May the 8th, EKU will grant us an extension. This class could go beyond May the 8th just to ensure that we do cover all the material required by the university. But I'm just giving you guys a heads up with that before we get to that point and we're still working on, say, May the 12th, and you're saying, hey, what are we doing? Everybody else is out of school. That's the joy of taking this college class. We lost last week due to the storms. We lost a week earlier because of the unplanned spring break, so we've got a lot of ground to make up. So I believe the last example that we did with this set of notes was example 4. So here we're going to go to example 5, and it says to consider the polynomial f of x equals the quantity x plus 1 squared times the quantity x minus 2. Find the x and y intercepts of the graph of f. Well, for part A, finding the x and y intercepts is not going to be too difficult. The y intercepts are when x is equal to 0. So let me just make a note here. We're doing the y-intercept is when x is equal to 0. So we just take our given function and we replace x with 0. And then we just simplify this. And what we end up with is 0 plus 1 is 1. 1 squared is still 1. 0 minus 2 is negative 2. So we get a y-intercept of negative 2. So that's going to be right here. There's our y-intercept. Now let's look at the x-intercepts. Again, that is going to be nice and easy because this problem is already factored. So we have x plus 1. We take the factors, set them equal to 0. X minus 2. And then we're going to go ahead and solve these for x. So here we get x is equal to negative 1, and here we get x is equal to positive 2. So I can plot those points on my graph as well. So I have an x-intercept at negative 1. I have an x-intercept at positive 2. And now we are finished with part A. Part B says to use those intercepts to find the intervals on which the graph is above the x-axis and on the intervals on which the graph is below the x-axis. So that's not a challenge so much that it can't be accomplished relatively easily. What we need to notice here is that from negative infinity up to negative 1, we have one interval where our graph will exist. From negative 1 to positive 2, we have another interval where this graph exists. And then from 2 to positive infinity, we have a third interval. So what we want to do is pick test points out of each one of those intervals, substitute it into our equation, and just determine the sign of the graph. If the sign is positive, then it lies above the x-axis. If the sign is negative, then it lies below the x-axis. So let's first look at the interval from negative infinity to negative 2. For this one, let's use a test point. Let me put down these intervals. So negative infinity to negative 1. Sorry, not negative 2. That's our interval. So let's test the x value of, say, -2, because that is within that interval from -infinity to -1. If I put -2 into the equation that we were given, I will get -1 quantity squared times -4, which is going to be just 1 times -4, and I get -4. So for this one, the sign is all we're interested in. It is negative, so that means that on the interval from -infinity to -1, the graph lies below the x-axis. For our next interval, it is from -1 to +2. We're going to pick a point in there. 0 is always really nice and easy to use. And we already know that answer because we did that when we found the y-intercept. When x is equal to 0, we get the y-intercept, and we know that will be -2. So again, because the sign is negative, this graph lies below the x-axis on that interval. And then we have our final interval, which is from 2 to +infinity. So once again, we pick a test point. 3 is in that interval. And we're going to substitute that into our equation. We get 3 plus 1 quantity squared times 3 minus 2. And what we end up with is 16 times 1, which is 16. The value isn't important, it's the sign on the value that is what's important here. So we get positive 16, so that means it is above the x-axis. So when we evaluate our test points, we're only interested in the sign. Negative means it's below the x-axis, positive means it's above the x-axis. So if we go back over here to the graph and try to determine what we can about it, we know that the graph lies below the x-axis from here to here, but it has to do something at this intercept. It has to touch or cross. But we also know that it lies below the x-axis from -1 to +2. So our graph probably is going to look something like this. We know it crosses the y-axis here, and then when it reaches +2, it's above the x-axis. These are just going to be sketches. They do not have to be exact, but they're going to be sketches of what we anticipate the graph to look like. So let's go to Desmos and graph this exact value and see if we're actually pretty close to what the true graph should look like. Sorry, I mean to scroll down through there. We have x plus 1 quantity squared times x minus 2. So I'm going to type this in. And here's our graph. I am zoomed way out here. Okay. So the what have I done? Okay. So the true graph, it's below the x-axis to -1. It's below the x-axis from -1 to 2. It crosses at -2 on the y-axis. It's close to what we have. The graph that's shown on the calculator is going to look more like what you're going to see here in pink. And so we weren't too far off with our sketch. But now when it just says to sketch the graph, then what we did was sufficient with the green graph. The pink graph obviously is much more accurate, but we did that by looking at the true plot on a graphing utility. All right, so if we talk about multiplicities, one thing I want you to notice on the example 5 is this term right here, x plus 1 quantity squared, has a multiplicity of 2. If you need to review multiplicities, go back and watch the previous video for this set of notes. We kind of touch on multiplicities a little bit. We're going to get into more specifics here right now. So numerically, if the 0 is of even multiplicity, so that means that exponent, if it's even, then what that means numerically is that the sign does not change from one side to the other side of r. In the previous example, the sign to the left of r was negative, so the sign to the right is going to be negative. Graphically, what it means is that the graph just touches the x-axis at that point. It does not cross the x-axis. So then when we talk about odd multiplicities, it's just the opposite. The sign will change from one side to the other. And then graphically, it means that the graph crosses the x-axis at that specified 0. So I'm going to go back up here to this graph. This was our 0 of -1, 0. It had a multiplicity of 2. As indicated by the square on the term up here at the top. And then the second 0 was at 2, 0, and it has a multiplicity of 1. That's an implied 1 as the exponent, which is odd. So at the even multiplicity, the sign is negative on the left, it's negative on the right, and it touches at that 0. It does not cross the x-axis, it just touches at that 0. The other 0 was at 2, 0, and it has a odd multiplicity. So it does change sign from one side to the other. So on the left side of the 0, it's negative. On the right side of the 0, the graph becomes positive. And as you can see, it does cross the x-axis at that particular point. So that's kind of a lowdown, quick run through on what multiplicities are when we're looking at evens and odds. The turning points of a polynomial function. If it is whatever the 0 or the degree of the polynomial is, remember that's the highest exponent, then the graph of that function will have at most n-1 turning points. That's how many times that graph can change direction. So if you look at the highest degree of the polynomial, for example, if it's a degree 3 polynomial, then it will have at most 2 turning points. 2 locations where that graph changes direction and turns in an opposite direction from where it was originally intended. So when we look at end behavior of polynomials, we end up with the same thing again. We're talking about similarities between graphs. If the graph is even, if it has an even degree, then it's going to resemble the x squared function. Both arms will be going up. If it's negative x to the 8th power, then it's going to resemble the negative x squared function where both arms are going down. And you'll see these as you practice some more. So if they have an odd degree, they're going to look very similar to the x cubed function. And that's how we talk about the end behavior of these. So they will closely resemble functions that we are already familiar with. If you take, for example, negative 2x cubed plus 5x squared plus x minus 4, that graph is a degree 3 polynomial. So its highest degree is 3, so it's going to probably resemble the graph that most closely looks like negative 2x cubed. And so what I've given you over here on the right is, in red, is the true graph of negative 2x cubed plus 5x squared plus x minus 4. In blue is the graph of negative 2x cubed. That's the function that we are claiming that it will be most similar to. Now the similarities that we're looking at here are not to draw an accurate representation of that graph, but it's to give you a mental idea, a mental image in your head of what that graph may look like. So if I walked up to you and said, hey, quick, what does the graph of negative 2x cubed plus 5x squared plus x minus 4 look like? You don't have to do a whole lot of thinking about it. You can just simply say, oh, well, that's probably going to look really close to negative 2x cubed. And you know what that graph looks like because you're familiar with the parent functions that we've talked about before. X cubed has the arms, one arm is up, one arm is down. And since it is negative x cubed, then we have to reflect it. So we end up with this graph that you see here in blue. whereas the true graph is what you see in red. The similarities are there. It's just a mental image of what the graph probably will look like. Example 6, we're going to take a graph and we're going to generate the polynomial that probably most closely resembles this graph. What we want to note first is that we have these zeros of -2, 0, 0, 0, and 2, 0. It's important to note also that at -2, 0, this graph touches the x-axis, but it does not cross it. So that means we have an odd or an even multiplicity. At 0, so let me just make a note of that, even multiplicity. At 0, 0, it crosses, so it has to be an odd multiplicity. And at 2, 0, it crosses, so it also has to have an odd multiplicity. The question asks us to find the polynomial function that has the smallest degree possible. Now, when we do that, we need to consider are the zeros of the function initially. So we have this first one over here on the left, the -2, 0. That implies that we have a factor of x plus 2. When you're taking a 0 and changing it to a factor, just change the sign of the x value and you have your factor. We also know it has an even multiplicity, so we're going to use 2 as our multiplicity of this function, or this particular, this 0. Then we also have this where it crosses the origin at 0, 0. So that's the same as x minus 0 or x plus 0, either one doesn't matter. But it has an odd multiplicity, so we're going to use 1 as the degree on this one. And then the third value where it crosses the x-axis is at 2, 0. It does cross, so it has an odd multiplicity. And just like we did with the -2, 0, this one will become x minus 2. And we're going to leave it as a degree 1 since it is odd, because the note up here says the smallest degree possible. We could have used any even degree we wanted to and any odd degree, but we're trying to find the smallest, so we'll use 1 and 2 for our small values. So there's kind of what this graph is going to look like. But the next thing that we want to look at too is there's probably going to be some coefficient. So when we set these up, I erased a whole lot there. We want to put a coefficient. In this case, we'll just call it a in front of this. And there is the general form of our function. Before we can continue, though, what we need to also look at is we're given a fourth point on this graph. When x is -1, y is 6. So we can use that to our advantage to come up with the correct function here. So if y is 6, when x is -1, we substitute in -1 for our x values. And we simplify this to find out what our coefficient should be. So we get 6 is equal to a times -1 plus 2 is +1. 1 squared is still 1. Times -1. -1 minus 2 is -3. When we simplify this further, we're going to get 3a. Divide both sides by 3, and we get a is equal to 2. So our polynomial will look like f of x equals 2 times x plus 2 quantity squared times x minus 2. And we can multiply this out if we wanted to. We would get 2 times x squared plus 4x plus 4 times x squared minus 2x. I distributed the x through the parentheses here. And then I multiply this trinomial and this binomial together. It's going to be a big long mess, so bear with me. We're going to get 2 times x to the 4th minus 2x cubed plus 4x cubed minus 8x squared plus 4x squared minus 8x. multiply all that by 2. Let's combine like terms as well before we do that. So this will be 2x cubed. These two terms will combine to be negative 4x. So now we can distribute our 2. We get 2x to the 4th. Plus 4x cubed minus 16x squared minus 8x. So there is the polynomial that would generate a graph that you see there on the left, just by simply using the zeros and one other given point in the graph. So here's a summary of the graph of a polynomial function. The degree of the polynomial is n, which is the highest degree of the polynomial. They are smooth and continuous. They have a maximum number of turning points of n minus 1. At a 0 of even multiplicity, the graph touches the x-axis. When it's odd, it crosses the x-axis. Between zeros, the graph is either above or below the x-axis. The end behavior is determined by what we would consider to be the parent function. If it's an even function, then it would have both arms up or both arms down. If it's odd, one arm up, one arm down, or vice versa, one arm down, one arm up. And y-intercept is found when x is equal to 0. So example 7 just says to analyze the graph of the polynomial function, find x and y intercepts, determine the zeros and their multiplicity, determine the maximum number of turning points, and sketch the graph. So let's first start out with the y-intercepts, because like I said, that's always pretty easy. We just set our x value equal to 0. So here we will get y is equal to 2 times 0 plus 1 times 0 minus 3 quantity squared. And here we get 1 times negative 3 squared. And that's going to be positive 9. So this graph crosses the y-axis at positive 9. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9. There's our y-intercept. Now let's look at our x-intercepts. Again, this one is nice because it's already factored, so we can take our factors, set them equal to 0, and solve for x. So here we would get x is equal to negative 1/2. And here we get x is equal to positive 3. So I will use positive 3 and negative 1/2 as my x-intercepts. I also note that on x equals 3, it has an even multiplicity. So we know that the graph will touch the x-axis at that point. Now I could do the test points like we did on example 5, but what I notice about this one is that it has a y-intercept between the two x-intercepts that I know of. So the only way that that y-intercept could be above the x-axis is if the graph is positive in this interval, and it would also have to be positive in this interval because of the even multiplicity of this 0. So it has to be above the x-axis. And then that means to the left here of this odd multiplicity, it has to be below the x-axis. So we're going to have something that looks kind of like, whoa, kind of like this, roughly. And that's all you have to do. Determine the maximum number of turning points, the degree of the polynomial. We have x to the first. This would be an x squared. Multiply x to the first and x squared, you get x cubed. So the turning points, actually let's back up and do the degree first. We just established the degree to be 3. So the turning points is 3 minus 1, which is equal to 2. So we have 2 turning points, at most 2 turning points, a degree 3 polynomial, and we have our zeros of negative 1/2 and positive 3. That's all you have to do with this. So analyzing the graph of a polynomial, determine the end behavior, find the x and y intercepts, determine the zeros and their multiplicity, determine the maximum number of turning points, and then you use all that information to sketch your graph. Now example 8 is one where it's not as easy to do because all these decimal values. This will be a hard one to factor using the algebraic skills that we have right now. So what I would recommend on this one is sometimes you do have to use a graphing utility to come up with the analysis of the equation. So here I'm going to have to go back and forth between these two. X cubed plus 2.48x squared. Let's see what else. Minus 4.315. All right, so this is what that graph should look like. If we wanted to analyze it using Desmos, you can simply click on the x-intercept here. It has one x-intercept at negative 3.791. It has a y-intercept at 0.2.484. And it's a cubic function, so we would expect one arm down, one arm up, and that's what we see here. The left side is down, the right side is up. And then if you wanted to further evaluate it, you can see that it has a maximum value or a turning point at negative 2.83 and another turning point at 0.63. Since it is a degree 3, it would have at most 2 turning points, and that's what we see here. And that's all you have to do. If they're complicated, use the graphing utility to come up with it. Nothing too fancy there. All right, so example 9, and I believe that's our last example, is one where you really do need to use the calculator. So I'm going to kind of try to do this to where you guys can keep up with what I'm doing. I need to write these values down real quick, so I'm going to pause the video for a second. All right, so I've written those values down, and now what I'd like to do is go back to Desmos. What we see here is it says that the table represents the weekly cost in thousands of dollars of printing X thousand textbooks. Use your calculator to create a line of best fit, and then predict the cost of printing 22,000 textbooks per week. So we have our first column is in thousands of dollars. Our first column is thousands of textbooks. And then our second column is in thousands of dollars. So we take that information, and if we go back to Desmos, Desmos will do this for us, but you have to be very careful how you go about setting this up. So I need to pull my keyboard over here. If you start out on a clean Desmos screen here, and you click on the plus symbol where it says add item, we're going to add a table. And then in the X column, we're going to have our values 0, 5. You guys don't need me to read them all off. Oh. Yeah. Struggling now, guys. Okay, so I've entered all my X values. Now I'm going to do the same thing for all of my Y values. Okay, so we've entered all of our values. If you notice over here on the right and the graph, those values did not show up. So I'm going to scroll out a little bit, and now you can see these values a little bit better. Now the question asks us to find the line of best fit. This does not appear to be linear. If you notice, this does appear to be more cubic in shape. It resembles the x cubed function as opposed to a linear function. So the the general form of a cubic function, I'm going to switch over again here, is going to look something similar to this. It's f of x equals ax cubed plus bx squared plus cx plus d. That's the general form. So we need to find the coefficients a, b, c, and d, and Desmos will do that for us. So here's how you do it with Desmos. In this second line down, we're going to just type in y sub 1. If you notice in our table, our x and our y values are listed with a sub 1. So we have y sub 1. Then you're going to use the little, I believe it's called a tilde symbol, or tilde, or I don't know. But it's the little squiggle, okay? So you have y sub 1 and then the tilde, and that's going to be ax sub 1 quantity cubed plus bx sub 1 squared plus cx sub 1 plus d. That was the same general form that we used that I wrote down for you a second ago. And if you notice at the bottom of the box here, it says parameters, and it has values for a, b, c, and d. So that would actually give us an equation that we can use to answer the second part of the question. I believe it was, let me look, predict the cost of printing 22,000 textbooks per week. So our value for x in this case will be 22, and we need to come up with the value for y using that information. So the a, b, c, and d are given to us now on Desmos. So we're going to type this in as a is 0.015459 times x cubed. Well, we're substituting 22 in for x. Plus b is negative 0. I will just change this to minus instead of plus. So it's going to be minus 0.595142 x squared. Well, x again is 22. Plus c is 9.15017 times x, and then plus d, 98.4327. And you can see in the box there, our answer is 176.30 is what we're going to go with, 176.30. So that would be the cost associated with printing 22,000 textbooks. It would be, let's see, $176,300 roughly to print that many textbooks based on the data provided. So all we did with Desmos is we found the values for A, B, C, and D. I replaced those in the equation that I typed in on the Desmos calculator. Whoops, I opened a new screen instead of Desmos. There we go. You can see those down again here in the bottom left, A, B, C, and D. And I just substitute those in for the A, B, C, and D in our general form of the equation. So I know that this is probably not the easiest thing to learn through this method of video teaching. So please, if you have questions, ask me. Look over the suggested problems and see how comfortable you are with them. Any of them that you have difficulty with, message me, and we'll do whatever we have to come up with a solution to show you the easiest way to solve them. Again, I hope you guys are doing great. I can't wait to see you all hopefully one day soon. I know it's not going to be during school, but maybe I'll run into you somewhere. Love you guys. You all take care, and I'll be talking to you.